Thank you very much.
Okay.
Okay, so first of all, I would like to thank organizers for inviting me here. So this is a great workshop and a very nice opportunity to present our most recent study done in collaboration with Andrei Galash, Rustam Alidjanov, and Vladimir Zakharov. In our work, we grow turbulence from small initial noise, random noise, within the one-dimensional nonlinear Schrödinger equation of focusing type, which is supplemented for the growth by linear pumping term. So this is the pumping term in the right-hand side of the equation. We wait until different levels of average intensity, chi square, are reached when turn of the pumping and study the resulting integrable turbulence. So how did we come to this formulation? A typical study of turbulence in an integrable system, also known as integrable turbulence, can be described as follows. First, we take some integrable system. Then we take specific type of initial conditions with some randomness. For example, modulationally unstable plane wave superseded with random noise. And then we study evolution of statistics in time, averaging the results over random realizations of initial conditions. Integrable systems allow conservation of infinite series of invariants, so that different types of initial conditions are characterized by different sets of integrals of motion. And during the evolution, they demonstrate different statistical behavior even in the long time. So from here, we can see that we can invent infinitely many such problems. We just take another type of initial conditions and get different results. Another problem is that in such studies, it is implicitly assumed that the initial conditions are somehow prepared by some external actor, and that resembles the setting of a laboratory experiment. In nature, we usually don't have such a situation. For example, if we consider water waves in seas, and waves are grown by wind in the same system where they travel later. In the present study, we mimic this situation. We temporarily add a small pump into an integrable model, making it non-integrable, wait until the average intensity reaches a certain level, and then switch off the pumping and examine the result in integrable turbulence. But for now, we are not interested in modeling real physical systems. We focus on studying the fundamental phenomena associated with integrable turbulence. Namely, one of the phenomena which is actively studied is the statistically stationary state, the state in which statistical functions are independent of time, statistical functions of a wave field. So its existence was suggested by Vladimir Zakharov, if I remember correctly, in 2009, and later it was corroborated in numerical simulations for some initial conditions. In those simulations, it was necessary to let the system evolve for a very long time because the initial state is typically far from stationary. In contrast to the studies, if we take small noise and small pumping coefficient, when it allows us to move sequentially through states which are stationary as soon as the pumping is turned off. So such a growth of integrable turbulence can be called adiabatic or quasi-stationary. And this approach allows us to study the whole family of stationary states from the initial weak nonlinearity to strongly nonlinear states. So in a sense, our numerical setting resembles an ideal gas in a box to which we add one molecule from time to time so that the system remains in equilibrium state and the state changes slowly over time. If we go to formulation of a problem, so this is the dimensionless system of equations which we solve numerically. We can, of course, consider different coefficients between dispersion and linearity terms, and say here some of our coefficients, but it is quite easy using the scaling transformations to reduce this problem to shown here. So here we start from small noise. The smallness of noise is governed by the coefficient A0. Its statistic is governed by the function fx. This function has unit characteristic spatial scale, delta x equals to 1, and unit average intensity. Here the overline means spatial averaging over the simulation box. We wait until the average intensity reaches level A final square, and then we turn off the pumping and study the integrable system. So from here, you can see that our results, by the way, we have periodic boundary. The period L is considered to be large. It's much larger than unity, when the characteristic spatial scale of a function fx. So from here, you can see that our results might depend on the initial and final mean amplitudes A0 and A final, noise statistics given by the function fx, pumping coefficient P0, and box size L. Our work contains two major parts. In the first part, we study statistical characteristics of wavefield by examining the basic statistical functions, such as Fourier spectrum, probability density function of intensity, and autocorrelation of intensity. In the second part, we solve the direct scattering problem, Sakharov-Shabbat scattering problem, for the grown-up wavefields and examine the IST spectrum. For first part, the methods are quite straightforward and repeated many times in our studies of integrable turbulence. For the second part, we will be talked tomorrow by Andrei Gelash, and he will be happy to explain all the details. So today I have a lot of interesting results to show, and this is why I don't cover the methods. I only talk about results. When the pumping is turned off, we have analyze equation of a focusing type, integrable. It conserves an infinite series of invariants, the wave action. In our notations, it just equals the average intensity, momentum, and total energy. The total energy is a sum of kinetic energy, and which is related to dispersion, and potential energy, which is related to nonlinearity. The ratio of potential energy to the kinetic one can serve us as a benchmark. So usually, if this ratio is small, so that kinetic energy is much larger than the potential one, when we can say that this is a mostly linear state. And if these energies are of the same order, then we can say that we are in a strongly nonlinear regime. When the pumping is on, these integrals evolve with time. For the first three of them, the direct calculation yields us with three equations. So wave action and momentum increase exponentially, and for the total energy, we have some non-trivial evolution. We focus on the adiabatic regime of the turbulence growth, which goes sequentially through statistically stationary states of integrable turbulence. And we may achieve this first when the pumping is small, so that the motion is governed primarily by the terms of the analyze equation, and when the initial state is already close to stationary. And the latter is possible, for example, when the initial wavefield is almost linear. For example, this is a small noise, because the linear turbulence is stationary. So now, to set the parameters of our simulations accordingly, we compare the characteristic time scale, so associated with the pumping, nonlinearity, and dispersion. And skipping the details, we come to these two conditions for the pumping. It must be small, and initial noise amplitude also must be small, so which is quite straightforward from what I just told before. Also, it is instructive to consider the equation of motion in a Fourier space. For adiabatic growth, we need to ensure that the pumping term in the right-hand side is much smaller than all the other terms present in the equation, including the dispersion term where we have explicit dependency on the wave number. This must be satisfied for all wave numbers, including the smallest non-zero ones, and from here we see this criterion for the pumping coefficient. And remembering that the box size is much larger than unity, this criterion is much more strict for P0 than the criterion I showed before here. So in the end, we arrived to these two conditions for adiabatic growth. This, of course, is a hypothesis, all of this, and so we have checked in our experiments that when these conditions are satisfied, the turbulence indeed grows adiabatically, and when they are not satisfied, we have non-adiabatic regime. So numerical methods, I will skip the details, just to explain that this function f, which defines statistics of initial noise, it has unit average intensity and unit characteristic spatial scale. We construct it as a superposition of linear waves with random phases Vk. So there is some spectrum Fk. It can be, for example, exponential if exponent s equals unity, exponent of minus k. Or it can be Gaussian, exponent of minus k square, or super Gaussian, for example, exponent of minus k at the power of 32. And all the time, the phases are random Vk. For each realization of initial conditions and also for each wave number k. I will focus on the experiment which I call the Bayes experiment. It shows adiabatic regime, so its parameters are shown here. So it has exponential, it has Gaussian initial spectrum, initial noise 0.01, final amplitude unity, and pumping coefficient 10 to the power of minus 5. For each of the several numerical experiments we performed simulations of time evolution in the formulation of those equations I showed before for an ensemble of several hundreds realizations of initial noise, which differ only in the set of random Fourier phases Vk. The amplitudes of free amplitudes of noise are always the same. And then we average the statistical results over these realizations. We have checked that large ensemble sizes lead to the same statistical results. We look at several statistical functions, for example, the kinetic and potential energies averaged over ensemble. For the moment, also known as Curtius, the probability density function of intensity, also the Fourier spectrum, which is normalized by delta K, and the so-called G2 function, also known as autocorrelation of intensity. So now the results. The left figure shows you the wave field at the end of a growth stage for the Wave experiment. You can see here that we have several pulses exceeding in amplitude exceeding 3 in amplitude. And this wave field has average intensity equals unity. So already from here, we can see that we have a lot of rogue waves. If you now look at the space-time evolution shown in the right figure, then we can see that these pulses do not move and stay more or less the same. So already from here, we can suspect that this is probably a soliton gas which contains standing solitons. If we now just fit these pulses with one soliton solution, we can see a very good match. So already just from the look of this wave field and from the look of how it evolves, we can say that this is probably a soliton gas, a bound state of solitons having zero velocities. Next, this is the statistical results. The figure A shows evolution in time after turning off the pumping for the potential energy, blue line, kinetic energy, black line, and the Curtius, which is red line. We can see that there is no time evolution here. So this is probably a stationary state. To be completely sure in this, we look at the 3 other functions. This is the wave action spectrum, then the PDF of intensity and autocorrelation of intensity. We look at these functions averaged over ensemble and also time intervals, but in 2 different time intervals, from blue line from 0 to 20 and red line from 80 to 100. And you can see that the lines coincide. So this is indeed a stationary state. We have checked, we have done the same test for intermediate stages of a pumping, and we observed the same result. So we can say that we indeed have an adiabatic growth. As soon as we turn off the pumping, the state is already stationary. Also, it is interesting to look at what we have at the final state. So the potential energy exceeds 2, the kinetic energy slightly exceeds 1, so the ratio is close to 2. So this is ratio of potential energy to kinetic 1 close to 2, informally known as the maximum ratio for stationary states. We cannot prove it yet. Also, the Curtius equals to 4.8, which is significantly larger than 2. 2, it is for a random superposition of linear waves. And also we can see that the PDF contains so-called fat tails. So we have a lot of rogue waves. And from our previous figure, we can suspect that these rogue waves are just solitons and the interactions. Next, it is that we have looked, we just saw the adiabatic regime, and let's play with its parameters. So let's start changing the pumping coefficient P0. And it turns out that if this pumping coefficient doesn't exceed 8 times 10 to the power of -5, we have the same results. So when we turn off the pumping at final amplitude equals unity, we have the same results. And when P0 exceeds this value, we have difference in our results as shown in the figures. And so it is interesting that this value, 8 times 10 to the power of -5, is just 3 times smaller than 2 pi over L squared from this criterion. So we can see just from here that this criterion indeed takes place in our system, that when the system satisfies this criterion, we have adiabatic regime, and when it doesn't, we don't have adiabatic regime. We have non-adiabatic regime. The same here, we change not P0, but L, and we come to the same conclusion. So if this criterion for L is satisfied, we have adiabatic regime. And next is what happens if we change initial noise amplitude. This is more interesting because in these 2 slides, here and here, those groups of curves with coinciding results, they are adiabatic regime, and curves that have deviations, they are non-adiabatic regimes. And here, all the curves including those deviating from the main group, they are all adiabatic regimes. And we have checked it by doing this tests as I showed here, and also doing experiments with different P0. We have checked, because for diabatic regime, it shouldn't be there shouldn't be difference if we go a little bit faster or slower, just if we are in a diabatic regime. In this case, all the curves show a diabatic regime, so all the experiments are diabatic. But it turns out that when the noise exceeds 0.03, we observe some difference in the results from the main group. So we can call this main group, with A0 smaller or equal 0.01 as the universal adiabatic regime, and the group with A0 exceeding 3 times 0.03 as non-universal adiabatic regime. And it looks that we have checked with our IST methods that for A0 smaller or equal 0.01, we do not have solitons in our initial noise. And when A0 exceeds or if it is equal to 0.03, we have solitons in some realizations of our initial noise. So this is probably the effect of different action of a pumping on solitonic and non-solitonic content. Next is that our results depend on the noise spectrum, on the initial noise spectrum. So this is the difference for different experiments. I will skip the details. And now it is the evolution of statistics when we grow the turbulence. So we turn off the pump and different mean amplitudes A final, so from 0.125 to unity, and look at what happens. So on the right hand side, you see here the potential to kinetic energy ratio. So for 0.125, it equals 0.0625. So the potential energy 16 times smaller than the kinetic one. Then this ratio increases quadratically with A final, and then it saturates to 2. And what is interesting is that, for example, if we look at A final equals 0.5, for this case, the kinetic energy equals the potential one. So we can say that we are in a strongly nonlinear regime already. And even in this case, the PDF of intensity coincides with exponential distribution, which is a benchmark of random superposition of linear waves. So we can see that we have a nonlinear system already here, but for some reason, still it has exponential PDF. Next is our IST results. On this figure, you can see the IST spectrum in some non-standard formulation. So it's not the spectral parameter, it is the amplitudes of solitons and wave velocities. This spectrum is shown for the same stages as on the previous slide. So from A final 0.125 to A final equals unity. There are several values shown in each figure. For figure A, the first value, 27, it is the total number of solitons detected. The second value, it is the ratio of a wave action or average intensity, which sits in the solitonic content only, divided by the total wave action. So 60% of all wave action sits in solitons. And the bottom figure, it is the average amplitude of soliton. So what is interesting here is that even when the potential energy is 16 times smaller than the kinetic one, so we are in a very weakly nonlinear regime, in a very weakly nonlinear state. Even in this case, 60% of all wave action sits in solitons. And when, for example, A final equals 0.25, so the potential energy is 4 times smaller than the kinetic one, we have 90% of all wave action sitting in solitons. This is figure C. And in the final state, we have 99% of all wave action sitting in solitons. Also, what is interesting is that when we grow turbulence, we see that solitons lose velocities and increase amplitudes. And from some threshold, they align themselves into one line. And this line is situated at 0 soliton velocity. So we are forming a bound state. At this final state, figure G, we have 95% of all wave action sitting into this bound state of solitons having 0 velocities. We have, for this figure G, we have 99% of all wave action sitting in solitons. So we can just forget about the non-solitonic content and just create the wave field for this solitonic content or solitonic content only, and compare this wave field of multi-soliton solution containing 95 solitons. We can do it with our methods with the original grown-up wave field, and this is the result. So you can see that the initial that the grown-up wave field can match very good with the multi-soliton solution. This experiment was for the Gaussian initial spectrum S equals 2. And let's look at what happens if we change the initial spectrum to super Gaussian S equals 32. And so here we have all the same observations, but in this case, all solitons, almost all solitons have the same amplitude. So this reminds us a conoidal wave. Also what is interesting in our results is that if we now compare two different realizations of a grown-up wave field, so this is the comparison on the left figure, we can see that we have strongly correlated parameters of solitons. So amplitudes and velocities are almost the same. So it is not just like that we have some range of soliton amplitudes and solitons have with amplitudes with some probabilities, but it is like that all the time we grow the same soliton gas with the same sets of solitons exactly, or more or less exactly. The soliton positions and phases, they do not show this feature. So soliton phases look uncorrelated between different realizations, and soliton positions have some distribution. So with figure A, left figure effectively shows that for universal adiabatic regime, we every time grow the same soliton gas irrespective of the Fourier phases of initial noise. And so this gas is defined by Fourier amplitudes of initial noise, not by the phases. Also, we have a hypothesis here that for adiabatic regime, phases of different solitons within the same wave field must be uncorrelated. So this idea, I think that Pierre Sourier will explain it in more details tomorrow, because he will have a talk about more or less the same idea he proposed several years ago. So also what is interesting to look at is that what happens when we deviate from the universal adiabatic regime. The left figure shows us the so-called non-universal adiabatic regime when we have increased increased amplitude of initial noise. And the right figure shows non-adiabatic regime with increased pumping coefficient. Main distinctions are that the distribution of soliton amplitudes is significantly wider. So here we have amplitudes maximum reaching about 6, and on the previous slide, here we could see that maximum soliton amplitudes were about 3.5. Next is that even at the end of growth stage, we can see that solitons, even large solitons, have noticeable velocity. So these states are far from being bound. And also for both experiments, we can see that different realizations of a grown-up wave field exhibit rather different amplitude velocity diagrams of a solitonic content. Could you please tell me how much time do I have? Do you hear me?
Yeah, you have about 3 minutes.
3 minutes. Okay, just reiterate the most unexpected conclusions for us, first of all. First is that conditions for adiabatic growth contain a relation between the pumping coefficient and the basin length. Significance, it is very difficult to create adiabatic regime for large basins. Second is this is the existence of what we call non-universal adiabatic regime when we have results dependent on the initial noise, and this is probably because of a different action of a pumping on the solitonic and non-solitonic content. Third, it is that for universal adiabatic regime, we do not see enhanced drop wave generation until quite late stages of a pumping. And next is that solitons start to dominate early. As I have shown you, even in the first stages, for which we checked the spectra, when the kinetic energy was much larger than the potential one, we have most of the action sitting in solitons. So the significance here is that soliton gas may be much more common in nature than we used to think, at least our group. And now it is that as the pumping continues, we observe that solitons increase in number and amplitude and form a bound state of solitons. which we call bound state solid and gas. And for universal adiabatic regime, we always grow the same solid and gas. We have the same solid and amplitudes and velocity. With gas depends only on the Fourier amplitudes of initial noise, but not on the specific set of random Fourier effects. That's it. Thank you.
Thank you. Any questions?
Nice talk. Just a couple of questions. First of all, your simulation just double precision.
Yes. Yes.
So, and when you determine this discrete spectrum, to determine this part of Elton norm, basically, which correspond to discrete spectrum by some version of direct scattering or something, right? So, question if it's sufficient precision for this, because your own work previously showed that multi-soliton solution requires high precision.
I understand your question. I just thought that you were asking me about a different stage of this work. I was answering on the evolution simulations. So for direct for analysis of direct spectrum, of course, double precision is not enough. We have used, I think, 1,000 digits, but Andrei Gelas should know better.
But simulations were done in double precision. You stop simulation and to determine discrete spectrum, you some way switch to much higher precision.
Yes. So the evolution simulations, they are done in double precision, and the analysis of direct scattering transform, it is with much higher precision.
Okay, thank you.
Any more questions? Okay, so let's thank Dimitri again.
Thank you very much.
We'll resume at 2 this afternoon.